Okay. So, say something.
Hello, hello.
Hello. So, yeah, your voice is on stream. I'm just gonna walk you through this. That way, I just wanted to get it recorded, so I don't have to walk
Okay.
through. Um,
Wait, r- are you streaming like here in Discord or in YouTube?
and YouTube. Oh, I need to. Why
Where's
did my
the-
stream here stop? Oh yeah, because I disconnected.
Yeah.
Okay. Da, 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 da.
All right, I'm watching.
Um. Okay. Cool. The. Okay. So with this, the you can see my screen now with this diagram.
Yep. Yep.
Okay. Awesome. So we have A on this half, and I'll just draw like a line down the middle so it's easier to see. And the hazards are all I really care about. Like these could be increments. It doesn't really matter what they are. It's just to get a point across. I know this is like a nonsensical thing, but like this green instruction comes into this first, and then this one would come into here, and then this instruction comes in, and then do you get that?
Yep.
Because like normally you write instructions like line 0, 1, that should be a 0, 1, 2, 3, like this. But when you're like writing out in these, I find it easier to go to this, and you can just like imagine them just dropping in through this. So that's the way I write it when I'm working through these diagrams. So you see that the green, like this green up here depends on this one, which depends on this one, which depends on this one, which you follow. Like there's like a
Yep.
chain.
Yep.
Um, So with a run ahead, what you would do is these two would be like if these two bottom ones are adds, these would just continue like normal because they're single cycle. But let's say this orange one, right, and that's a horrible, horrible color to write with. Is white better? Yeah, white's a lot better. So if this instruction is a load, it's gonna take maybe like 4 cycles, right? If it's a cache hit.
Yeah.
Or like maybe let's say like 32 on miss. 32 cycles miss. Okay, so then you don't know exactly when you can issue the next instruction, and this is where and like variable memory latency is the prime example of when this kind of stuff comes into effect. Because you don't know when you know optimally you're gonna get it in 4 cycles, but how often do you get things optimally? Not that much. So for out of order, like you asked earlier for Thomas Julius, you do the renaming and all that stuff to get around it. But for the run ahead, what I would do, with the way that I'm doing this run ahead system, when this instruction here goes to issue, so this start instruction, it's this one right here. Um, Instead of being issued, when it gets to like, so let's say give me just a second. I'm going to erase this brush 14. So we have green instruction coming through the pipeline, right? Let's say um say this is the line where you start executing. Okay? So you have green, green, then you have this yellow, which doesn't commit because you're waiting on it. So this is just kind of like off down here somewhere, right? This is going to come back at some later point. So then this next yellow, what it would do is instead of executing when it gets to this cycle, which I'll dash gray. When it gets to this cycle, this one will then get piped up here into a separate queue structure, and you would just keep that instruction up here. and then you wait until this load comes back, and immediately once this load comes back, so if this load comes back on this cycle, it finally goes, cool, I'm stored, then you start issuing this yellow instruction here. 1, 2, 3, 4, 5. So you would reissue this instruction at a later date when you know that it would be, which is the standard out of order. But instead of renaming, I just push these to a queue. So these instructions always have to be issued in order. So like if I have one load, then another load, then another load. But like if I have a load that takes like 20 cycles, and then there's like something else that comes in, and you're still waiting on that, and a load that comes in that only takes 4 cycles. Well, if you have the instructions waiting on the 4 are going to be behind the 20, and that's where this would be slow. Is where if you had discrepancies of things head, and that's fine. I don't care. That's an edge case. I don't give a shit. I'm not renaming. I'm not out of ordering that severely, and that's the whole point. Is when you start renaming and stuff like that, there's a lot of complexity that adds to the pipeline. As far as like, there's a lot of other random things to get added to the pipeline, and the whole idea of this is to try to see if I can make it more efficient, and like increase my IPC. Because like right now, before we increased our IPC, because you could do a load and then you could just do some random instructions after that, and you didn't care what they were, because like as long as you didn't mess with that register, you were fine. But now you can mess with that register. You can try to write to that register once, and you can infinitely read to that register. Well, not infinitely. You can read to that register as many times as your run ahead queue will allow before your cycle stalls, before your system ever stalls. So you can just build up a bunch of stuff and just keep making forward progress. So even though you are like the load of 4 cycles on this is like waiting behind the load of 32, even though this is done, that's fine, because a lot of instructions were hopefully done in the time that this 32 cycles are actually being waited. So there's actually work being done in that time, so it doesn't really matter that it's waiting. As long as there's work being done, that's the goal.
Mm-hmm.
So I'm just trying to saturate my pipeline as much as possible without renaming. And that means I
So
can
it's
go ahead.
run ahead is just pushing instructions to a later date,
Yeah, is literally you're
pretty
just like
much.
running ahead of your current hazard point.
Yeah. Okay, that makes sense.
So yeah, and there's like so since this is not stateful, because there's out of order issue and out of order commit, this is in the no land we talked about during like last
Yeah,
summer.
I remember the chart that you put at the top right.
Yeah, the no land, like you don't
The
want to do
no
out of order
land.
issue and out of order commit. However, I have specific fencing instructions put in the pipeline that allow you to like just flush the run ahead queue and say, okay, no, we're just ending here, or to wait until it, or stall until it empties. So you can force just, hey, no, we're stopping, because like you hit like a terminal hazard in the thread, so it doesn't even matter about these instructions. You can just kill it. Or if you know that you need to safely go on to another program, you can then say, hey, I want to fence here, and the CPU just waits until all the entire pipeline is caught up to where you are.
Wait, fencing is for IO, right?
No, there's multiple types. So fencing is just any way for so a fence is a software mechanism to stall a CPU until some structural event happens. But it's not like an interrupt or an exception. It's more you're like voluntarily stalling for a structural hazard to clear. And like for instance, if I swap over to like I have the fencing instructions on pORC2, yeah. So the pORC2 data fence load, data fence store, data invalidate, instruction fence, instruction invalidate, and then full fence, full invalidate. So what these all do, so in a data fence load, it makes sure that all pending load instructions are entirely complete. And so I'll have like a little I'll have a queue to set up just to monitor for pending like active loads and active stores. And those you can just wait until those are completely done and you know that they're written to memory. Data fence load store allows you to fence on both of them. Data invalidate just destroys all the stuff in well, invalidate does a full fence, then it flushes the L1 data cache. And then instruction fence allows you to wait until you catch up to your current point. And then instruction invalidate is the fence, and then it flushes L1 cache. So you can make sure that all your data is actually written back to either in this case, L2 is just going to be memory, like straight RAM. But L2 is usually like the level up where you're stored. It's not private. It's like public. Like L2 cache is public. So the idea is that if you'd have like a more shared L2, is that this invalidate instruction would make sure that you could guarantee that everyone has your current up-to-date data. Then there's full fence, full invalidate. The one thing that I'm curious about is the yeah, no, I'm going to keep that. But yeah, these allow you to forcibly wait. So if you know you did like a load and then a bunch of random work, and you just want to make sure that that work is completely done, so you want to make it atomic. So you want to have like an atomic operation, you can do like a full fence instruction. So you wait till all pending loads and stores and all pending instructions are done. Then you do then you issue your instructions, then you do another full fence, and then you can put the rest of your instructions. And that guarantees that there's a stable state in the fully stable state before those instructions start and after those instructions are considered finished. So it allows me to get around the fact that it's not really stateful. And since the instructions I don't have any states between instructions. Like you have to check for carry, overflow, borrow, check. I did that on purpose. So I don't have to worry about exceptions. You have to check for your own exceptions. And by issuing these fences, like if you know you're about to do something that could cause that, you need to like fence and then do a syscall to like request permission, or fence and then attempt it, check, and then like run a fence to see, okay, did that actually succeed? So you're gonna have to actually like, it allows you to, it does mean that if you're trying to do like super like multi-threaded stuff on a system, the fencing, the invalidation and flushing, that will actually like, I think will help a lot for that. But the individual like core could go really bad, could really mess with the system if you let the run ahead queue get too deep. But yeah, like you could just have like 1,000 instructions that just used like, you could have like 1,000 instructions that used like 3 registers, right? And it just kept abusing, like reading those 3 registers over and over and over and storing them to memory or whatever like that. And you just kept adding to a register over and over and over. And since the increment was like instantaneous, all you had to do was wait. So then for like one hazard, and so it's to clear, and like all these instructions are in your run ahead queue, and you did some other shit. It can get funky. Get in some weird unknown state. Like if you stall the CPU at a single cycle, you have no idea what's actually the current state of the program. Because even though your program counters are like 17, you've committed instruction 14, but you haven't even issued instruction 3. So it gets
a
you
lot to wrap around your head.
Yeah,
it's like for out of order. There's so many things happening. It's the hard part. Just picturing everything happening in your head. So what are you working on now?
I am
like a part of pORC2.
So part of this is like before on pORC1, all we needed was a single dirty bit in the registers, and that was the entire state of the register, right?
Mm-hmm.
But for pORC2, you're allowed to go 1 deep. You're allowed to work around like 1 deep write hazards. So if you load to register 5, then you want to use register 5, you push you want to write to register 5, you push that write operation to the run ahead queue, and then you push any writes from then on to the run ahead queue as well. But the next write operation that goes to register 5, that second one would stall the CPU until that load comes back, because you only have one pending write out, like in flight at once. Otherwise, you need to track a lot more state, and you get it pretty much into renaming. And like, I do have there is some renaming involved, but it's not really like renaming. It's just, so when I have the stat cache and stuff like that, when you write, so what I'm working on today is we figured out the state machine. Let me pull that up for the new registers, instead of just having a single dirty bit where it goes dirty clean. And it was just multi-cycle issue, multi-cycle write back, and that was pretty much it. And you would stall if you try to write again from dirty. But now you only stall if you try to write to pending write status, and you have this whole like mess of states. And zero register, I've decided to add a state machine to as well, so that way if you want to securely like stall based on some value, you can. So if you want to like load a value to a register, and you just want to know if whenever the value comes back, you don't really care about the value at all, you can just load it into the zero register, and you know that even if someone's tried to send you like a malicious value or something like that, it didn't matter, because all you were confirming is the receipt of the value. You didn't care about the value. And there's no way for your software to accidentally see it, because if you try to read from the zero register, you're just gonna get the zero register. And like the one thing we did have in we look at this forwarding mux. Forward detection is what I want to look at. Yeah, okay. So right here I have, so in pORC1 there was kind of, because of the way the pipeline worked, and there wasn't that much out of order in the issue on the commit. There wasn't any out of order issue stuff. Well, there I allowed you to forward through the zero register, so you could write values to it as like a trash location and know that the next time you read it, it's still going to be 0. So you didn't have to worry about like clearing something afterwards. You could like do some math, write a partial value. You could like write a partial value to there, and then like immediately read it out, and it'd be fine. But since there's run ahead, you can't guarantee that instruction A will always be directly after instruction B. So, I had to put this here, which prevents you from forwarding whenever you're writing to a zero register, but it still allows you to work through this, like the state machine. So you can still stall on the 0. So you can be like, hey, I'm gonna load to 0, and then I'm gonna read from 0 or whatever. Yeah. But yeah, and then today what we're doing is this. The whole idea of the stat cache is allow you single cycle access to your stack, and up to like 16 tangential addresses plus or minus your current stack head. But actually no, just like you can just go like 32 deep into your stack at any time, and you can like move your stack pointer and stuff like that. You can just play with it essentially. Like you can work on your stack with single cycle penalties.
I didn't even know stack cache exists.
I don't know if it does. I made it in Minecraft one time, and I worked on an old state machine for it. But that was without out without run ahead. And the whole idea behind that was in Minecraft shift right, and in like the whole idea was let me bring out Milton. So we have each cache line consists of let's say in this example we're gonna have four values per cache line, right? So that way your stack, if you're pointing to like this instruction here, you're in one line. So in this cache we have 4 lines. Okay, we have the current line you're on, which is going to be underscored gray. Then we have the +1, which could be here, and you could have the -1, which could be here. So this would be the one ahead of it, one below, and this is the this is the to be replaced, right? So this is like it could be a +2 or a -2 or whatever. So it could be plus. Hold on, I need to go with a smaller pen size. So this +1 +2 -2 -1. So this is prefetched. So this is prefetched. So if it sees that you jump from here to here, so if you go bink and you move into this, then this one automatically grabs the next location. Does that make sense?
Yeah.
So since like the whole with memory prefetching, it's really nice because you can go ahead of your program and stuff like that, and you can find addresses. But that involves some complicated ass like maneuvers and stuff to guess addresses. But when you're working on a stack, you modify your stack pointer occasionally, but a lot of you're not changing it like every instruction. You're changing it every like handful of instructions maybe. But this allows you to almost guarantee that your stack is always going to be here. So and then whenever you do change your stack pointer, it flushes this cache and replaces it. So even though that would take maybe like 4 cycles, because the whole idea is that the bus width would be equal to a cache line, so it fits with the L1. It's the same width as an L1 cache line. So I just transfer out in 4 cycles, and I grab the new one, your new one, in 3 cycles, marking this one invalid. So then I would have like the new, and then new +1, and then new +1, and new -1, and it would just grab those locations from memory, and it would and it would just allow you to move through them.
Yeah.
That way, even though it would give you like a 7 cycle additional latency on that one on the instruction after you changed the stack pointer, that's fine because like you get single cycle access through it. So as long as you're not changing it every like 4 instructions, then you should be getting a net positive. If my math is right, that could have gone the wrong direction with that. But yeah, every time I've used a stack, I've pushed like maybe 10, 20 values to it and then roll through it. And with my cache lines being 8 deep, I know I'm going to have at least 32. I'm going to have 32 values that I can push into my stack cache and get near instant access. And since the idea is that this is directly connected to L1 cache, either the L1 or L2, so that way as you grab values, as you're like loading values into this will just grab your L1, L2 bandwidth and just grab in the +2 or -2. So even if you're pushing more than 32 things into your stack, it still should be able to mimic your stack access being 1 cycle each, as long as you're not like hammering everything else. But if I have 8 instructions, if 8 data elements fit per line, and you do and you're doing like a mass load into a register, and this top of the stack is mapped to the stack, so loading into a register pushes into the stack, you're effectively doing a memory to memory operation with that. It should be able to keep it up because each one of these will need to will hit a cache miss every 8 cycles. And as long as they're both prefetching, as long as like the L1 cache is like prefetching one ahead, and this automatically does, so it's fine, then you should never actually reach a point where you're bottlenecked because this will issue for 8 cycles and it would get back. It's like once it would take 1 cycle out and 1 cycle back, and then this would pipeline right behind it. So yeah, the idea is that you can. I'm trying to mask stack access latency with this. And with that being said,
It's a neat trick, though.
huh?
It's a neat trick.
Yeah. So the whole one of the interesting things is that because a stack isn't necessarily the same value each time. So if I have like if I go to write a value into the stack pointer at like register 7, right? At like address 7, and then I issue another instruction. It goes to 8, and then 9, and then 10, right? And it just keeps going down here, and then you want to pop, right? You want to start using it again. This could have been a load, so if you the instruction that uses wants to use value 9 is now pending, right? So this instruction needs to go to the run ahead queue, right? But that means you would have to stall. However, I'm going to use what I'm going to do is I'm going to send, instead, I'm not going to directly rename. I'm going to send the index, the index that matches this 32-bit, wherever it lands in this 32-bit range. I'm going to send that ID out with this to the run ahead queue. So the next time it comes around, it knows it needs to write to this location. So that way, if you want to reuse the stack again, you check the status of entry 8. And if entry 8 is valid, you can just keep on trucking. So you can interweave your dependencies really, really tight. Like, you can pretty much do pseudo renaming through like reverse Polish notation if you interleave like your math with reverse Polish notation properly. So that's my goal, is interleave. My idea is to get a stack cache mixed with proper state management, mixed with run ahead, to give me like pseudo renaming that could be really, really smooth and only really there when you really need it or really want to use it, but doesn't give you the huge bottlenecks when you don't. Huh?
What? I didn't say anything.
Oh, I thought your mic activated. So to circle around, today what I'm doing is I want to take the state machine we made for the individual registers, and I want to adapt it to work for each one of these entries. And I think it may just be the same entry. So I think it may just be the same thing for each of them, but I'm not exactly sure. So yeah, this does introduce, like, the stack cache is the largest will be the largest structure in the entire CPU, hands down. Beside, like, even though it's 32 values, it'll probably have take up the same space as like a 64. No, as like a 48 entries cache, just because of it has a lot of metadata it needs to store for these things. But I'm willing to take that. I'll happily take that. So I don't really care, because right now my run ahead queue, I only plan to run it at maybe 32 deep. So each counter on these only really needs to be like 5 deep, worst case, 5 or 6. Yeah, 5 bits. I'll make them 6 bits just to make sure that they never overflow. But you're always going to stall if you try to issue something to the run ahead. So that way, the pending read counters will never get higher than the pending reads, higher than the depth of the run ahead. So I can easily just minimize that overhead. Yeah. So, by the way, yo, you understand that this is not normal run. Like, this run ahead that I'm doing is not this per spec, like the spec of the paper. And this stat cache is just like something I've really, really wanted to do. And it's only like on this project that I realized that these two could potentially have a really cool, like, they could meld really well together. So, do you know what actual run ahead is?
Is it the same thing you explained earlier?
No, so the run ahead I explained is my interpretation and variant on run ahead. The actual version of run ahead, whenever you would hit like a hazard, like you would hit like a cache miss, like load to R4, right? Or load to 4. And then you would go to like you go to add 4, right? Add R4 here. That would like cause a hazard, right? And what the CPU
Yep.
would do is it would say, okay, cool, this is my checkpoint. It stores this location as its known like pause point, and it starts running ahead in the program, trying to grab as many load instructions as it possibly can and generate those addresses. So it just tries to pretty much, so it stores the register state, it like duplicates the registers real quick, and then it just runs ahead and pretty much looks at all and just tries to generate all of the cache misses it possibly can, which is essentially what I'm doing. But then once they do that, they and they'll assume, I believe the whole mechanism is like there's some so you end up going through, you generate all those, and then once you get this load back, you then dump out your queue, and you just pretty much then you resume from this point. So I want to get rid of this resume, and I just want to like say I'm just gonna actually execute this queue. And the reason they don't execute this queue is because it makes your system unstateful. Like I mentioned, you don't know what registers or what at any given time. You can't just stall the CPU and know what's happening explicitly. So that's why they just trash these values and roll back the CPU state, but they keep the L1 cache. So then as these instructions are coming through, a compiler will normally give you like 2 cycles of latency or whatever. You tell it to say like, hey, yeah, and I know like if you compile just standard RISC-V or x86 code a lot of those times, they'll just give you 2 cycles. They won't ever use a load immediately. They'll wait a cycle or 2 and then use it. Because they're assuming like they're hoping for L1 hits and hoping that it's 2 cycle additional latencies. So the idea is the run ahead is that if you follow those same compiler metrics and you put the same code through this, you spend that time stalling. And if you spent like 100 cycles stalling for this, the idea is that you probably are going to stall for more things in the future. So you make sure that no matter what, even if the things, maybe something you need in like 5 cycles got evicted because of this 100. Well, now it's going to be brought back because you ran ahead. And you know when you issue your code the second time, every single load you do is going to get a hit, or hopefully get a hit. Does that make sense? So you just effectively you just roll ahead to try and generate cache hits, because variable latency instructions are the entire thing that the out of order optimizes around. And like the fastest multipliers, the fastest dividers, whatever, you can estimate those as being like X amount of cycles latency. But when it comes to like different types of loads and stuff, you can assume a cache level 1 hit of like 2 or 4 cycles or something like that. But more further out than L2, that's a crapshoot on how many cycles it's going to take. It's a total crapshoot. So the out of order will work around that variable latency. This will just say, hey, I know that latency's there. Let's just try to prefetch. So it turns your full CPU into a prefetch engine, essentially.
What's up, dudes?
Not much.
Yeah,
Hey, hello.
Hey. So just to wrap up my thought real quick. So my idea is let's keep this and just add fences to the CPU. So if you ever want to know where your state is, you can just cut it right there and let everything like catch up to itself. Do you see where this fencing fits in now? Like more clearly?
I feel like I understand your system more than I do the actual run ahead, but I can always rewatch the stream.
Yeah, all they do is throw away everything in the run ahead queue the moment the hazard clears, and then roll back to where they started filling it. That's the only difference. I issue from the front of mine. They use that clearing as a way to like roll their system back to maintain a cleaner state. Does it all make like more sense?
The last statement you said made sense. The trashing the entire run ahead after a hazard is cleared.
Yep. Then they just roll the system back, and I don't do the rollback because fencing. And because it allows me to play really nice thing. It allows me to do this cool thing with my stat cache. This stat cache thing would not be possible with this, because you would have to roll back memory states. I'm allowing you to fuck with your memory state because I maintain order I maintain programmatic order, so I don't care if those get a little messy. The biggest issue with this system would be if you lose power while you have stuff that's pending and out and stuff like that. That would be the biggest issue. But for that, you just have a write through cache, and that can be managed. Like, it may require you to like force you to put in an like a flush instruction every once in a while. Just make sure, like, hey, when you go, this is going to be like your known rollback point. But I don't know. There's always a difference between using files and saving files for a reason, I suppose. You may just have to restart your process, but it should never like write over something. If you're going to actually do a hard write to storage, you should like get confirmation. Which, I mean, if you cut power on a modern system in the middle of a write to storage, it's pretty much going to be like, I hate you anyway, and you're going to corrupt that write and have to reattempt it. So yeah, I don't really care. I think the benefits far outweigh the potential data struggles.
Yeah.
Writing a compiler for the go ahead.
Yeah. I'm looking kind of off topic, but I'm kind of looking at your old register, the one with the dirty bit thing. Why does your mux have 2 memory data ins for the conditions?
For what? Wait, what were you looking at again?
You're for pORC1, right? You have a register file cell, the one with the dirty bit.
Yeah.
Why does your register mux have 2 memory data inputs?
Oh, my register, because we have the in order pipeline and the out of order pipeline.
What?
Remember,
Wait,
we
I'll show
had
you.
the
I'll screen
pORC.
share.
We have like when you remember the dirty bit, the whole thing how you have like the memory reads. One
Yeah.
one of those sides is from memory.
One of those writes is from memory. Yeah, there's a data in and a memory data in. But then there's also another condition that is memory data in.
I'm not sure. What are you on pORC1?
Yeah, hold on. I'll screen share.
Are you on the development branch or the main branch, by the way?
This looks like this is the development branch.
Okay.
You see it? This one.
Hold on, it's loading.
Yeah.
Oh, that's just in case if both are on at the same time.
Oh, okay.
Yeah.
So it's just the
Yeah,
Alright,
in
thanks.
case both come on at the same time, it prioritizes that. That's like if that's just it should never happen because of the dirty bit, but in case you get into some weird mode where it does happen, Even though that
Okay,
probably should
thank
go to 0, so you know more likely of what that something went wrong, but I don't know.
All right, thanks.
No problem.
Okay, rename time.
Guys, Midnight Ghost Hunt is free right now on Epic, and I want to play that game so bad.
Midnight Ghost Hunt.
Yeah, it's, you know what Prop Hunt is?
Steam. No. Epic Games.
Yeah, on the Epic Games launcher. Yeah. Have you ever played Prop Hunt or heard of Prop Hunt in like Gary's mod?
I've heard of Gary's mod, but I don't play games anymore.
So Prop Hunt is just something where
sadly.
you decide that you are going to be something, be like an object, and then you have to like try to hide from somebody else. You have to hide from the people hunting you, so you can be like a cabinet. If someone discovers that you're a cabinet, then game over.
How would they know that you're a cabinet?
Because I think you have to move. Like you're not allowed to sit still for X amount of time.
Right.
I can't remember. There's some, yeah. I think like when you become it, like it automatically moves a little bit, so it's gonna be out of place. You have to like put yourself back in place. People have to like look for. I don't know. I've seen people play it. It's really fun. I can't really pinpoint. Yeah, everyone I've seen it says they have a blast. And Midnight Ghost Hunt just seems like cool, but I've never been so invested in it that I would pay $20 for the game. But since it's free, I'll definitely grab it. Yeah, the idea today is to go through the stack, and based on what I was saying here, I think when I was reviewing this, I think it's actually just gonna be best to use the same state machine for this entire thing for each one of these entries, and then just have like a state for the cache line that just checks, is everything clear? Are all 8 values clear? If they are, then that's a clean cache line and I can eject it if I need to. If not, then I just can't. Yeah. So yeah, I'm just gonna do that. So the state vector, I had these, and then yeah, I'm just gonna assign the pins.
For the rename counter, do I just increment every single write?
Yeah, you can just rename increment every single write, and then the instruction you can use the name of the instruction as the name of the write back operand. They can be like the same.
All right.
You don't have to tag them separate. Okay. So then in the stack, let me look at the pipeline.
Wait, are the rename counter and the rename table are separate, or can I just use one?
Well, they can be in the same module, but like
Alright.
the rename table is a table of pretty much your registers of So if you have like 8 registers and you need 8 entries, and if your tags are 5 bits wide, then you need 8 registers of 5 bits each, and that stores plus a valid bit. So you need 6 bits in that case. Your upper bit you set to a 1 whenever you know that the value in the register is completely valid and good. But if that value is ever a 1 or ever a 0, then you know that the lower 5 bits are a pointer, or not the pointer, but the name of the instruction that's generating that operand. So if you have an instruction that's doing a load register 5 and register 5, that instruction gets named like 62, then you know that the R5 is now named 62. So the next instruction that wants to come through and read R5 gets renamed with the rename counter, and then while that's happening in parallel, you check the read operand and say, oh, R5 has name 62. So you just pretty much throw away that it goes to R5. You don't throw it away, but you ignore it for now. And you just focus on listening for instruction 62 to write back its value via the common data bus. And once
so you have,
go ahead.
You have like a dirty bit for the rename counter? Is that
For the
what
rename
you're saying?
for the rename table per register.
You have a dirty bit.
Yeah, you have a dirty bit in there essentially.
Okay.
And that dirty bit just set, and if that dirty bit is set, or a valid bit, if that valid bit is not set, or the dirty bit is set, depending on which one you want to use.
What are the conditions for it being valid? Like for a new commit.
What happens is, like, the common data bus, when that load 62 comes back, its value gets broadcast over the common data bus along with that tag of 62, right?
Yeah.
And that it's register 5. So what you would do is you would then look at you would go to register 5, you would write back your value to register 5. You would then, any instruction that's in the reservation station needing 62 would grab your value and mark their operand valid. And finally, you then send that 62, that register 5, 62, like that pair of values, into the rename table. If register 5 currently has the value 62 in the rename table, you then validate the register or mark it clean. Because you know that the most recent, like, in-flight write instruction is now completed, and there's been no writes since the last time that instruction went through the rename system. On that note, I'm going to get up and take a stretch break.
Bad idea.
I said I'm moving too far. Get it gone.
You literally join the moment I click on, like, stretch break. Give me 5 minutes, RT. I've been explaining run ahead and out of order stuff to YOLO in chat, for YOLO in voice, while going over, like, the stack hash design at the same time.
Said I might be big in a game like she went and got them breast implants. I said I'm moving too fast, didn't even get a glance. I'm ready to eat up track like I'm seated in a restaurant. If you had swag like mine, you know it's best to flaunt. We aren't hating because you aren't shining like it's neon, rock like kings of Leon. Shooting stars across the galaxy. I stand out, so don't be mad at me. Infiltrate, I'm with my strategy. When I turn up, then I just have to leave. Shooting stars across the galaxy. I stand out, so don't be mad at me. Infiltrate, I'm with my strategy. When I turn up, then I just have to leave. Yeah, shooting. Yeah, shooting. Yeah, shooting. Yeah, shooting. too far. Get to glance.
just to know what you knew. Restless every time we start locking eyes. Lost control. Oh, it's paradise with honesty, but I'm in the dead of the night. Let the darkness take control. Let the darkness take control. Darkness take control. May the darkness take control. Take me in the smoke, breathe me in and let me go. Sink to your heart to find you. Open up your eyes till you're blinded by the lies, so you can see what you do. Restless every time we start locking eyes. Lost control. Oh, it's paradise with honesty, but I'm in the dead of the night. Teardrops on the floor. The pain is over. Feel the darkness take control.
Yeah. There we go. I added a filter to it a couple streams ago. It probably made it way too loud. That's honestly probably why I went from like averaging like, 'cause I used to get like 50, 60 views in between, like within a couple weeks of a few of the old streams. And then the last handful have been like 9. But also I've been really inconsistent. Yeah. It's definitely not a norm. I'm gonna post something in the OR staff chat real quick. One second.
Thank God that the brothers on the rise now. Endless celebrations all in my house. Levitating now, I'm super duper fly now. London boy, but they see where I reside now. Put the time in while you always yelling time out. And quit it, cause I know I'm coming with it. You were sitting, you were wishing I was handling my business. Now I got the ball like Harry Potter playing Quidditch. And my business is humongous, you would think that happens in it. Damn man, I'm all that, yeah, I'm all that. Working for that whip, yeah, that what you call that. I'ma blow up in the summer, have him yelling fall back. And I've always been ahead like an effing ball cap. Man, I came in the game like, whoa. Gotta cut chains on me cause I like gold. They told me I'm the best and I told them I know. Cause when I'm in your town, every ticket I sold.
I'm asking if I can leak something that's not gonna be announced till like 3 p.m. Like change what I'm working on stream to being something else. No, it's the next competition. Les does not want me to leak information, so I'm gonna call this here and then go work on that. One second. But yeah, I mainly wanted to, my goal today was, I knew I probably wouldn't get through things, but actually explaining the whole like run ahead thing to YOLO, like solidified like that, yeah, the state machine we made will work. So like that makes me really happy, like it makes me even more confident in it. Also going through this stack stuff with him made me even more happy, and I didn't even realize that like my goal was to work this in there, but having the ability to like push to the stack with an operation and then do another operation that pushes to the stack, as long as there's no like A to B dependency between those operations, you can just keep doing them and then operate on them in a different order, like going down, and the run ahead queue will allow you to just operate on those values out of order. So your stack can just dynamically move, and then like at a later date, all those things will just catch up to each other. Right? Yeah, so it gives you like full out of order stuff for your cache, for your stack, which I almost feel like is more powerful. That plus the basic run ahead, I feel like, oh, the IPC improvement, I feel like could be actually rather high. Yeah. I really, really like this. Yeah, so I think one of the two craziest things are the new run ahead, run star, I'll call it run star for now, which run star, and then the stat cache. Those are the two fun things. I'm so excited to see how well those play together. With any luck, they play very nicely with each other, and then on pORC2, the goal would be to make this like a 2-wide issue system. Because we'll already have the RISC-V CSRs, so if we get the basic CPU running all nice and clean, changing this over, if it's running the RISC-V CSRs and already doing all the privilege, the stuff required for privilege stuff, swapping it over to a RISC-V instruction set enough to run something like Linux wouldn't be very difficult at all. So that may be like a side thing from pORC at some point. Once we get this to a really far point, we're really happy with it, I may make a separate version that just changes out the instruction encoding for RISC-V. But yeah, I am very, very hyped for this. I'm so looking forward to, like, I want to try to see how many people I can get to write programs with it, just to see what type of performance I can get out of it. Like, I'll probably spend time, once this is done, actually, this is the first CPU that I've been, like, personal project CPU that's, like open source project, that I'm really excited that I want to actually write a bunch of software for and, like, find test benches. Like, known, like, good quality testing stuff. Yeah. I definitely want to see what this can do. Like, what I want to see is, I would love for, yeah, I want to find like a comparable CPU that seems like it has somewhat decent specs or takes up the same amount of like resources on an FPGA, and see what kind of IPC I can get at the same frequency. I would love to be able to do that. Oh yeah, no, because I'm only single issue. So if you're single issue, you can only, the max IPC you can get is equal to your issue width. That you just can't go faster than the rate of instructions you can put into it. So that's why my idea for this one is to see how close I can get to 1, and then if I get to, then adding the second one, making it 2 issue, the goal would be to try and sustain at least 1 on average. Obviously, with like if you're doing memory heavy stuff, it's hard as fuck to sustain that if you're thrashing your cache a lot. But if the combination of the run ahead with the stat cache allows some like really fancy, allows my IPC to get at 1 or something like that, it would never get to at 1. That would be a pipe dream. But if I get to like 80% with a 2 wide issue, that would make me beyond happy. Just space on the chip. So right now I'm like, we have that 1K of fixed RAM that you can use as like a scratch pad that will always be like 2 or 3 cycles. Doesn't matter what, like whatever memory pipeline I think it is, going to be like 3 or 4 cycles. Yeah, it's going to be a fixed latency constantly, and you get like 1K of memory of that to use minus the IO space. And it's up to the kernel whether or not they want to allow you to access that or not. But the idea is that even if the kernel uses like 512, then you have 256 mapped to IO, the next 256 mapped to IO, then the upper 256 you could give to users to use as their own 256 entry, just 256 byte scratch pad that they have constant access to. And then they have that plus the really good stat cache. So the idea is that stuff for like short-term memory could go into the that 256, and then you could have you could use your stack as like a transport mechanism. If you wanted to move like a bunch of like 128 bytes from your main memory into that memory structure, you could do like a load store, but you're going to like saturate the amount of registers you use, because you can only if you load like the same register twice, it's gonna give you a problem. So you can only load as many registers as you have until you start running out of like your metadata. So let's say you have 16 registers, you can only run ahead like maybe 12, because you need like 1's a 0 register and 3 for your like indexes and stuff to keep track of. So with that being said, you can only go so far ahead. But with the top of the stack map the way it is, you can iterate and do 128 loads to register 14 back to back to back to back to back to back to back. And if they're sequential, great. Then the prefetch on this L1 data cache and the stat cache is going to do you just fine. And it's going to wind up, and then it's going to be every single cycle perfect saturation load into the stat cache. Then immediately from there, you do another 128 dump from there into the half of that memory, the 256 scratch pad you want. And then you've used 256 cycles plus 4 for the boot up the initial latency of going to the scratch pad. So that's 260 plus whatever latency you had for your initial load, and that's essentially your cost of doing that transfer, which isn't that bad considering you're doing a load and store. So unless you have a memory to memory system, you're going to need 256 operations anyway. But the fact that this makes it 256 operations plus 4 plus whatever inherent latency your memory has, which you're going to have regardless, the idea is that this could get you to like a really good high throughput like mass memory transfer. Yeah, these two together, and I'm happily keeping this entire fucking thing open source, because even if I don't write cool shit with this, someone you wants to use these ideas and make a cool CPU, oh my god, I'm gonna put a license. And the license I think we picked before, but I'm gonna put it on there of being the one that you just have to attribute me if you use anything for it. So there's like a trail. And that's all I want. I just want a trail so I can see where it goes. I don't care what you do with it. I just want a trail. That's all I want to see. I want to see if anyone ends up using it for anything. Because that'd be awesome if like top stat cache ends up being used for in any cool stat projects. I was gonna just use like the built-in Libero, built-in like RISC-V CPU that Libero has, and then like the new RISC-V Nios from Intel. And the goal would be I would compare it to those using my instruction set, and then later on, once I got it solidified, that's why I wanted to go swap it over to RISC-V fully later, because then I could do an apples-to-apples comparison. Versus if I clock theirs at 100 megahertz and mine at 100 megahertz, and they both take up like 1500 ALMs for the core CPU, do I get a higher IPC? And if I do, then fuck yeah, I'm gonna be really happy. I want at least like 10-15% more. I'd be happy with 10-15% more. Yeah, IPC per ALM essentially. But yeah, I really kind of am hoping that these things work. This would be really cool if this works out as well as I hope it does. Yeah. So yeah. I find it really fun. I'm on like ramble mode now, but I'm gonna end the stream and then I'll ramble to you more and go over that other stuff. But yeah. Bye, YouTube.